Hey everybody, this is Larry. This is me going with Q4 of the weekly contest 471, Sum of Perfect Square Ancestors. Hit the like button, subscribe button, join me on Discord. Let me know what you think about this one. This one is a very, this poem has a lot of theory, if you want to call it that, in the sense that it's just a lot of knowledge, right? Let's go over a few things really quick and we'll just go over a few things very quick, right? The first and I was able to get this in about 12 minutes, and a lot of it is just because I do know all these things already. So it's a little bit of a hey, you should practice, I guess, right? But just because you practice doesn't mean you get it, but still, it helps you a lot. So the first thing to notice is that what is a perfect square, right? Well, a perfect square, there are a couple of things that's about it. The first thing to note is that for a perfect square, maybe 16 is equal to 4 times 4, right, etc. But another way to think about this is that 16 is equal to 4 by 4, equal to 2 to the 4, right? Or maybe another perfect square. What's another perfect square? Let's say 255, right? It's 15 square. Well, 15 square is also just 3 square times 5 square, right? Or maybe 3 times 5 square, maybe depending on how you want to say it, all those things. But what is a square, right? A square means that, and maybe going back to the 16 case, 2 to the 4, so that looks like 24, 2 to the 4, given 2 to the 4, it just means that the exponent is even, right? Because it just means that it's 2 to the 2 to the 2, right? So it can be any x, right? 2 to the x to the 2, or any p, really. So any p to the x to the 2 is what you're looking for as a perfect prime. And keep in mind that this applies, extends, right? This extends a little bit. In the sense that then now, this also is equal to p sub 0 x, p sub 1 of x sub 1 to the 2, right? So that's basically the core idea for a primary thing. And the reason why this is interesting is then that means that that means that for this particular problem, we'll skip the tree part until later, but the idea here is that we're looking for, I think the tree part is actually not that interesting in a way, because the worst case is still going to be a linked list, or you can think about it, a linked list, but it's essentially an array. And given an array, the key thing to do is just not to make it n squared, because n is big, right? But keeping in mind that when you have something like this, then what happens, right? That means that so this is a square, right? So squares, but you have numbers that are like p sub, where basically in here those exponents x sub 0 can be odd, right? So then what happens? That means that, well, if it's odd, then we just have to multiply it by another p sub, okay, maybe it's not p sub 0 anymore, but actually I guess it is p sub 0 of another, like y sub 0 from another number, where y sub 0, where y sub 0 is also odd, right? Because then now, if x sub 0 plus y sub 0 mod 2 is equal to 0, how do I 2? Oops. Is mod 2 is equal to 0, then it is an even number and we're Gucci, right? Because you're multiplying them, so you add the exponent, etc., etc. Okay, so and if that was too fast, watch it again, is what I would say. And that's the first part. The second part, actually, I still need my thing though. Right? So then now, the second part is that, okay, now we establish what a perfect square is. Then, and we also established a little bit, maybe I didn't go in detail, we established that given a number, right, let's say t for target, is just equal to some prime to some exponents, right? And we're also like, yeah, and that's it, right? Actually, now that I think about it, I think there's a better. I could change the way that I was writing it, but in any case, yeah, so then you have this, and then the idea is that, okay, let's say this is t of 1, and then now in the future we have another number. Well, and all we have to do is just try to figure out a way such that we, again, this is using the array. No, we'll ignore the tree for now. The tree part is just an implementation detail, to be frank. But you're just able to do it in all of n times or n log n times or something like that, right? And then the idea is that, okay, well, we're just trying to figure out in the past of all these things where, you know, where, so we're trying to make it so that y sub 0, y plus 1, and y sub 2, dot, dot, dot. All of these could be odd or even, but we want to make it so that we want to match them, essentially, in that, you know, if this is even, then the previous one should be even. If this is odd, then the previous one should be odd, and so forth. And given that each number can only be odd and even, then, well, we can reduce this even more, right? We can just say, instead of this, as a number, as an exponent, we can reduce this from to x sub I has to be, you go to 0 and 1, right, in the set. And in that set, I guess this is not set notation, actually, but whatever. You know, and y sub I also in that set, just to keep it consistent, right? And given that, well, one is that you could say that the 0 drops out, right? Because you're trying to match with something that doesn't exist, for example, right? For example, you're also matching with all the zeros, right? So that's fine, right? Meaning that, for example, if this has a 2 to the 6, it doesn't, t2 does not need any 2's, right? It could have 2 to the 0, or 2 to the 2, or 2 to the 4, or whatever, dot, dot, dot. But that's fine, right? So that's and so then now you can reduce this furthermore by just looking at where x sub I is equal to 1, and then just keep track of all the things, because then now you have this, and you have this, and let's say these are all odd, and you're just trying to match all the odd ones, and that's it. Yeah, and then just count the number of things. The tree thing is implementation detail. We'll talk about it in a bit. I don't think it's that interesting, but yeah. Yeah. Okay, let me turn this off for a second. Okay. So first of all, this is the prime CIF. Definitely Google this. I'm not going to go over this video because there's a lot to go over, and also it's pretty standard-ish. So like most, probably there are a lot of good videos out there. Is my point, right? And the one that I use for this particular problem, if you watch me live, I usually write this on the spot, and sometimes it leads to silly mistakes. But I usually write whatever is pertinent to the problem. So this is what I have, right? So yeah, so prime sub I contains a prime of I, right? I think you can make it so that it's the smallest, if you like. I think the way that I end up writing is the biggest prime of I, but it doesn't really matter. The idea here is that you can chain it, right? The usage of it is so that we could chain it. We'll show you later. Actually, it's here. But the idea, okay, we'll just go with that code then, right? And the idea of this is just that it gives you one prime, and prime sub I is a prime if prime sub I is equal to I, right? And that's it. And then I have this function that it's a cache function, but this part just based on the idea that prime sub I contains a prime of I. It technically doesn't matter which prime as long as it's a prime, just to be specific, because then now, and in a way you can, and we'll use a real number. What's a good real number? Let's say 60, right? 60, right? So maybe a prime could be 5, right? And there's 5, so maybe, you know, we call this function prime of 60 is equal to 5 times prime of 12 is equal to 5 times, I don't know, 2 times prime of 6, and then goes, you know, 5 times 2 times 3 times prime of 2, and then at the very end we get this, right? So that's kind of the way that you degenerate it or deconstruct it. The key thing to note is that, for example, the biggest number is 10 to the 5th, which is less than 10 to the 6, well, which is obvious, but I say 10 to the 6 because it's easier to remember. That is 1 million, which is 2 to the 20. 2 to the 20 means that this number has at most 20 chains, right? Because if it's a million, then it's not a million, but like 2 to the 20, which is a little bit over a million. If you have that, and it has to be less than that, so you could even have tighter bounds if you want to construct it out. But it means that this will have 20 numbers, right? That's just an upper bound, that's all. That's basically the idea. The idea that I have here is that we're trying to create a hash for this number, right? Because as we said, S contains the set. We want to remove P, and then we want to add P, right? So the first time that so you could think of S as the set of things that this number has an odd prime of, which it needs and also can give, right? And what I mean by that is just like if you pair two numbers, if they have a number in S, then it needs that number. We'll go over what I mean by this in a second, and there's some optimization that we can do here, right? But we'll do that later. We'll go over the tree part. The tree part, like I said, is not that interesting, but I want to go over it before we go back to the hash part, because it makes sense. And again, the way that I thought about this is just with an array, but with rollbacks, right? Which is how a tree, you can think about tree as a recursive structure, where like, you know, that's why they call it a core stack, right? So you implement the tree on the stack, and as a result, then, you know, you could keep certain states on there. You know, it's pretty standard, I think. Maybe not. Let me know in the comments. But yeah, but first of all, we construct a tree adjacency list for the tree. We set up the ancestor, right, for counter. For this one, we start off the root of node 0, no parent, -1, and then now we just get the answer. Okay, so here we give the current number for the node, so it's node 0. We get the current number that's in the thing. We get S, which is this thing, which is basically all the numbers that has a prime, all the prime factors that has an odd exponent, right? That's it. So that two things can happen. One is that this part, right? So okay, let me write it down actually. S is the list of numbers with list of prime factors with odd exponents, right? And now that means that now we are able look through the ancestors and see if there are other of the same one, right? Because that means that, because for this one, for it to be a perfect square, every number has to be even, right? So the even numbers are already even on both sides. So that means that to basically cancel out or make all the odd things even, you just kind of like map it together. And basically that's why you have S. So that's basically what this does, is that it just counts the total, right? And then here, it is basically setting up for the future, right? Set up ends so that it declares that we need these things, right? These things to make a pair, to make perfect square, right? And keep in mind that if you have one, the set is actually empty. And it, yeah. For now, let's think of this as a set. We'll go over some details in a bit, right? But yeah, we set it up as a set. But the problem is that, of course, a set, you can't really use a hash thing. So that's why we have to do some things. But you can think of it as just a thing for now. And then now this is just recursive, right? A tree, we set it up. We do a recursion. At the end, we roll it back because now you're popping back to the parent. So you want to remove S, because now it is not the ancestor of anyone anymore, right? And that's it. Then going for now with that context, right? Now with this context, to go here, yeah, you can have S. You know, we remove P, we add P, right? And that's it, right? We move, we add. This is the dividing thing that we talked about. And then at the end, we just convert it to a string, to hash, right? It's a list of, and we remember, you have to make sure that it is sorted, right? And stuff like that. But now that I think about it, you don't even need to do this. Because what was my running time? Let's see real quick. Okay, it doesn't say. Let's give a quick submit. Maybe then now it would say. Yeah, actually this is pretty fast. I think. I don't know. It doesn't really tell me my percentile. I guess that's fine. But yeah, but actually, I think an observation that I noticed as I was writing this, is that because we only it's a list of prime factors, that means that with odd exponents, that means that this number, when we or all these set of things, we can return a number that represents this, which is just the product of everything, right? So basically now you have like key is equal to 1 for C and S, key multiplied by C, and then now we just return K, right? Or yeah. So this one took 64. Let's see, it should be faster, right? I mean, we do, yeah. So this is faster, and less memory, I think. Actually, I don't know. I don't know why Leetcode is sometimes weird. But yeah. Keep in mind though that of course we cache everything, and there's only 1 million of these, so just so that we don't need to do it again, right? But not a big deal. Yeah, or less than 1 million, 100,000. Sorry. So yeah. So what's the complexity? That is the tricky part, or that could be a tricky part if you're not familiar enough with this. But yeah. So for every node, we look at each node once, right? Just to be clear, pretty straightforward, right? We look at each node once. This is a regular, you could say depth first search, recursion, tree traversal, literally. So yeah, like, yeah, right? The only thing that's a little bit, I mean, this is linear, this is a tree, so the number of edges is also linear, right? What I mean by that is if n is the number of nodes, the number of edges is also n, right? O of n technically is n minus 1 because it's a tree, right? So yeah, the only thing that may be looking a little bit tricky is this function. But as we said, this function at most is 2 to the 20, and technically it's more than that, but it's 2 to the 20, so it's at most O of 20, or you could say maybe O of b, where b is the number of bits, right? So relatively fast. So it's going to be, because then now it's going to be 20 times n, right, at most, and that is going to be fast enough. But that's just this function though. What about the pre-processing, right? I'm not going to go over prime sieve in this video, but suffice to say that this is of course, I don't know why I said of course, but this is actually n log n, well, maybe max log max if you want to call it that, m, right? It is just how that works. If you want to see a proof, definitely check those videos out. But yeah, and again, we said that this only calls up to 20 times, and on top of that, we actually cache, so we do not recalculate across different problems. Same as here, actually. So that's why it is fast. You could imagine that we don't cache, and it still should be fast enough, I hope. But you can definitely see that it'll be slower, right? It's either that or the inputs are too easy. I guess the inputs are too easy then. I'm a little bit surprised, actually. But it is a little bit cleaner because we did clean it up. Maybe it's a little bit more. We kept everything to string. But that's it. But that's it. That's what I have for this one. Here's the prime sieve. Here's the prime list generator, if you want to call it that. And here's the tree. And yeah, that's what I have for this one. Let me know what you think. Thanks for watching. And you can watch me solve it live during the contest now. Yes. Okay. That is the stupidest way to get a wrong answer though. That is actually dumb. I feel so bad on that one. Like I got the hard part and I got the silly part wrong. Okay. Let's see. Sum of perfect square ancestors. Okay. Integer n, undirected tree root at node 0 with n nodes. Can't believe I got it wrong on the dumbest part. And I don't even need it apparently. No, I guess maybe I do. I don't know. Why doesn't that work actually? Whatever, we'll think about that another time. Okay. just have edges. That's all this is saying. You're given an integer. Num sub I is the positive. Okay, so we have nodes, we have edges, and you have some value associated. Define t, but such that the product num sub I times number of ancestor is a perfect square. Oh, it's a tree rooted. Okay, it's a rooted tree. Ancestors, number of ancestors is a perfect square. With the product is within the sum, t sub I is the number of ancestors of node I, and then sum of all of them. Okay. I guess n could be pretty big, and we have an edge, basically a linked list. Then it's going to be not a great time, right? How do I write this? Without checking all the previous ones, right? Guess that's the idea. Well, 10 to the 5th. So what does that mean? There's 1,000 squares, is it? Or less than 1,000, right? So there are 1,000. Can we check 1,000 for each of the n? No, that's too much. So, I have to draw this. I mean, I don't have to draw this out, but I should draw this out. So you have 2a2. Right, and then 2 times, oh, it's the product, not the sum. So we just have to track the evenness, the odd evenness of numbers, primes up to 10 to the 5th. Well, not primes, but obviously not primes, but just like we could. Oh yeah. I don't think this is that bad. You just keep track. Pass it down recursion. Yeah, okay. Yeah, okay. What are we doing? What are we doing? Right, and then now we want to whatever, right? We want to get, yeah. Can nums be 1? Okay. Does 1 matter? 1 is weird. Yeah. No, that's fine. Yeah. Yeah, okay, fine. Yeah. 1 is still number though. Weird though. Okay. And then now we just want to store a bit mask, right? So, but we it's recursion. No, so you shouldn't pass a bit mask. Maybe you should. How many primes are there on the top? Like a lot. So we want Okay, this is one. I mean, all this is semantics. I think this is not that bad. Yeah, this is not that bad. This is not that bad. Okay. So the current is good. Let's look up. Let's just say we have. Maybe that's right, guys. Let's say ancestors. Yeah. Okay. So then now we have to get get prime of the for some x, right? So then now it's just no, I think it's fine. I'm trying to optimize too much. I think that's right. I think there's a better way to write this, but I don't know. And next, right? And then we return s. I don't know if this is. I think this should be fine, but. I think this should be fine, but I might as well just clean it up and cache this. Okay, so then now s is equal to this, right? Then now we're counting the ancestors. Is this the sum or the sum, right? So then now total is equal to 0. We can say we can just pass it along, I suppose. I don't know. Either way is fine. Right? Oh. I think there's a million times I forget how to write. Yeah, and then of course. Not answer. Yeah. We know, and we are Gucci, I think. 3, 1, 2. As long as we're not running out of time for some reason. Do I have some silly loop that I don't know about? P could be 1. When would P is equal to 1? Well, this is dumb though. Alright, that's much better. 312, is that what I said? All right, that's YOLO submit. Okay. I mean, not so bad. Very dumb mistake on Q2. I feel so sad. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's farm, this contest, everything in between. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye-bye.